some of the instructions in the setup of the 8051. And the reason I'm doing that is because you've had some time to work through some of the labs and see how things are going. And come on in up there. So by repeating, I think it might sink in a little bit more this time. Now that you've seen it once before, you've had a chance to play with the board, you've done a lab. Yesterday, I would have to think that the experience of actually having to type most of those instructions in, you could get a little bit better feel for what's going on versus last week when I just basically gave you the code. So that's there. I have not come up with a lab for next week yet, but I hope to have a similar type lab next week. It won't be as long. And the reason it won't be as long is simply because one is I'm not lecturing on it so I need to fill in the little briefing for the lab, and then the lab all within the same 2-hour block. And at the same time, we've got a week break after next week, right? So, and I assume everyone's looking forward to going out of town or going home or whatever you're doing for that period. So, okay. So as I said, I'm kind of backing up here a little bit, and I'm going back to these original slides So I'm really going pretty far back and again, I'm stealing these slides from this gentleman in Taiwan. He actually did a pretty good job, so of it as well. Okay, we've looked at the registers right there, and we use the registers a lot. R0 through R7 right there. We use those a lot right there. And so I'm going to talk a little bit more on the registers, and in particular how we switch banks. I started without you, I'm sorry. No. There. I got a question. Some of you have classes that run right to 10:15, and then you have to rush to the next class? Because I noticed yesterday that I had a class before me in that room that ran right till right till 10:15. So I think some of the some classes actually run the full 2 hours I never run the full 2 hours when I'm lecturing, but as you noticed yesterday in lab, we were there pretty much the full 2 hours, and that's typical. Where I came from last time, our normal lecture pattern were 2 50-minute lectures a week, and then 1 2-hour to 3-hour lab period. We set aside 3 hours, but most of you could do it in 2 hours. That was a typical class structure. Okay, we talked about the registers. We've seen the registers, and for those who just walked in, this is a repeat lecture. In other words, I'm going back and covering some of the same material over again. Now that you've seen it in the lab and you've played with it, let me go through it again and kind of highlight the things that we saw. So we used the registers a lot yesterday. We pumped a lot of information in and out of the accumulator, in and out of B, in and out of memory, in and out of So we used registers right there. So the register sets are 8 bits wide and we discovered that, we realized that they were 8 bits simply because we were trying to do 8-bit multiplication, and doing 8-bit multiplication and only having 8-bit registers meant that what would have been a one-line program in C became about a full page in assembly language right there. So when we look at that so our registers are 8 bits. They're set up D0 through D7 data bits So this is the common structure of the registers right there. We used A and B. Remember, when we multiply, we had to use A and B. Whenever we add, we have to use A. A is the accumulator. It is used for almost all arithmetic and logic. That is our number one register right there. So almost anything we're going to do is going to use the accumulator right there. B is its next door neighbor. So A and B are the easiest two to use. Then we have a set of 4 registers, R6 or R0 through R7. We used those a lot yesterday, right there. We also have 2 others that we really didn't use yet, and we'll use them later. One is the data pointer. Now the data pointer is a 16-bit register. It's got 2 halves to it, and we use that for indirect addressing. And I need to come up with a program where we use indirect addressing right there. Because indirect addressing is used, for example, if we want to add up 10 numbers there, or if we want to load a string in and output the string to a LCD display or a terminal or something like that. So we there, and then the program counter is also part of our widely used registers, but we don't write to the program counter ourselves. We almost never change the program counter ourselves, nor do we read it. That's maintained by two things. Well, first off, the microprocessor itself, whenever it reads an instruction, it will increment the program counter accordingly to whether or not it's a one instruction that's there. You know, something like move AB only requires one op-amp, or one opcode, excuse me, one op-amp, one opcode. But a long jump requires three. It needs an opcode for the long jump, and then two bytes for the address where you're going to jump to, right there. So not all instructions have the same number of bytes attached to it. That's there. So when we look at the program counter, that's maintained by the microprocessor. The other place the program counter is maintained by, again, it's maintained by the microprocessor, is if we have a long jump or a long call, then the program counter is loaded in by the address we put in there. We don't change the program counter, but by using the instruction long jump to main, which is what we use at the beginning of our code at address 000, we have, our first instruction was long jump main. That tells the microprocessor to load in the program counter the address of main, wherever main is in our code, right there. So, okay, we've talked about the move. I'm not going to go into that there. This is one that I made a mistake on, right there. Some of you caught that yesterday. Is in my handwriting version of our code, I said we had to move 0 into location 32 or 31 and 30, right? If you remember that there. No, all of a sudden my sinuses are plugging up again. Haze is coming around. There, my throat. I think the haze is coming back again today. I don't know. It doesn't look bad, but my sinuses are plugging up and my throat's a little itchy. Right there. So, if you remember, I had some instructions that said move to location 31H0 right there. And we've discovered yesterday that caused problems. And the reason it caused problems is I forgot the number sign there, the hashtag. Now, if I do move 31H0 without the hashtags, what am I telling the processor to do? I'm telling it to go to location 000 in the data memory and take whatever's there and move that to location 31X right there. So if this contains 20, I move 20 there. If it contains 10, it moves 10. I don't know what it is, because when I first turn on the processor, memory contains garbage right there. Right there. So this is the instruction. We wanted to zero out memory location 31, because we wanted to add to it any, got there up, it's a little stuffy back there, right there. So that was a mistake that I'd made when I wrote that out. So this again, it points out that they're moved to the destination and then the source. Now the source, here we have various ones here. Again, they're showing the hash mark there. This, we're moving A into these registers is what we're doing. Right there. Right there. So, again, this is just some things that I know I went through these before. There, again, this is highlighting the hash mark. This is also highlighting the fact that if you start with our memory, if our memory location code is A3H, we have to put a 0 in front of it right there. That's all that is saying right there. Everything else up there. Now, this particular one, and I know I went through this one once before, Here we're trying to move 16 bits into an 8-bit register. Our compiler will spit at that one right there. So, okay, the add, we've gone through the add. We've spent a lot of time on the add. I'm going to kind of skip over that there. Now, kind of going through the process, and this process is very easy today, but when I first, one of the first computers that I played with, and it was actually an old computer when I got my hands on it, was a computer called an Altar. Now the Altar was based on the 8080, one of the first microprocessor that Intel sold directly. It was sold as a kit. It was about this big, right there. And you started the Altar up by flipping switches on the front, zeros and ones, and hitting a load button. Flipping switches, load button. And you would enter your program 1 byte at a time. And then you would go back and put the starting address in and hit the run button. Very tedious. Very tedious. When I first started teaching microprocessors, I used the 8085, which was the second generation, and we would program these by using Knox. Life got a little bit better. Instead of having switches that we did, we had a hex keypad that we would enter 3A, enter, 3A, enter, 3A, 2B, enter. And we would enter our code 1 byte at a time. That's there. So, assembly language allowed us to write our instructions in something that looks like something that we can read. Some people say it looks something like English. It doesn't look like English. It looks like some garbage language right there. That there. But it is more readable than ones and zeros and hex code. When I look at something like move a number 0 right there, that is different than 2A00. 2A is the there, and I made 2A up. It's not the actual instruction. Just simply move A into A, immediate X there, and then the second instruction is the data that I want to move into A. So we have a series of opcodes for that there, and assembly language has done that there. Now, the way that I learned how to program is I would write in assembly language, and then I would pull up the card that had all the opcodes, and then I would hand assemble that there. So that there. So I have a mnemonic followed by 1 or 2 operands. The mnemonic is, again, abbreviation, easy to remember. That's relative term, whether it's easy to remember right there. But moving to A immediate is mnemonic right there. Optionally followed by 1 or 2. If I move into A the number 0, I would follow it with 0. If I move into A the number 5, I would follow it with A right there. So given assembly language, but if I say I wanted to move to address 30 hex, the number 29 hex, for example, that would require 2 operands. One is the operand, you would have one mnemonic for move to memory immediate, and then you would have the memory location, and then you would have the data. That would require 2 pieces of information. So that instruction requires 3 hex numbers right there. Something with like multiply AB, that doesn't require any data because the data is already in A and B. So this would only be 1 instruction, or this is 3 instructions. So the size of the instructions varies greatly there. So we have 2 things. We have the actual instructions, and then we have the directives. We've seen those. We've talked about them before, but again, I'm taking today as just kind of a day to go back and highlight some important things that we've talked about right there. So what this is basically saying that this is basically a small set of code. It's a little different than what we're seeing, but we have org0 right there. Org0 simply is telling the assembler that that's where we want to put the code. That is not an instruction. That's a directive. It doesn't, but that just simply tells the assembler, and more importantly, the linker, that that's where this code is going to be, right there. These here are our opcodes. Mnemonics, they will produce opcodes, right there, and then we also have our data. right there. This, these are things such as our data right here. There. We also used some labels yesterday, right? We used a lot of labels for do not add. We did a jump no carry. That goes to a label. Now a label, all a label is just something that the assembler kind of keeps in mind when it writes the code. It will translate that when it converts it to machine code to the actual address of that instruction. So when we go back and we look at our code it'll just translate to an address, because this is address 00 right there, and then this address goes on down, and this is address, say, 35 hex right there. We don't know what that address is. So when we say jump here, it's a short jump to address 35 right there. So as we go through here, so we've got three things that are pointed out here. We've got the label, the mnemonic, operands, and then of course I haven't talked about comments. Comments is a very important part of assembly language programming, because the code is very cryptic, that if you don't comment your code, later on you're going to read it and try to figure out what's going on. We haven't talked much about commenting code, but commenting code is a very important aspect. I worked for companies that had a very strict format for commenting their code. Everything had to be according to a company policy on commenting code. That's there. When I first started working for that particular company, I thought it was a pain in the neck, as most young engineers, when they are faced with with instructions, you must do it this way, not the way that you want to do it. That there. But then later on, I discovered, as I was stealing other people's code, when I use the word steal, I mean I'm going through the library and I'm going through and borrowing functions so I didn't have to rewrite them myself, which was the reason they required these comments. That's there. Everything had to be commented very well so that other people can reuse your code. Right there. Just as I'm sitting here right now using Dr. Hanel's slides, which he graciously put up on the internet for people to, I don't know if he put them up deliberately for people to use, because I don't know if I told this class, I was searching for slides to use, and I discovered for one of my other classes, and what I discovered was a bunch of my slides were put up on the internet by somebody. So I put them up like I do for my classes on a website. I didn't put them up on file sharing sites, and someone put them up on a file sharing site for me. I don't care, because I didn't copyright them, and I don't care if people use my slides, just as I have to assume he doesn't care that I use his slides. The same thing in company software libraries. We've got, I'm working for General Electric at the time, is who I was working for as a consultant, and I was writing a bunch of code. It turns out that I was writing this code not in assembly language, but it was a language called Rocky Mountain Basic, which doesn't even exist anymore. But when I was writing this code, I would have to comment it a certain way that other people that were writing code could go through and steal my routines and use them there. As it turned out, that particular job, I worked on it for about 4 months on a project. They canceled the project at the end, but all my code stayed in the library and was still being used 4 or 5 years later. So the program that I wrote ended up not being implemented because the manager that was in charge of that particular said he wasn't going to have his engineers do that type of work. That there was nothing wrong with the code I wrote. It was just the manager didn't want to do it. When I was hired, he didn't want me to do it. But that was above my pay grade. I just went ahead and developed the software anyway. It worked perfectly fine. He just said, I'm not going to do it. And then all the engineers that worked for him went and sold the parts of the code anyway, and were still doing it. The manager ended up getting fired 2-3 years later because of something else similar. But my code stayed in the library. So even though the project was canceled, the code was still there. It was still used. So commenting is a very important part of code right there. So, all right, the steps that we go through. This is written back in the Dark Ages. The way we do it today is much simpler. But I'm going to go through this there. First, we use an editor to type our program right there. Okay, when we bring up wherever it is here, all apps. Right there. When I bring this software up right here, let's bring up, this is a C code right there. Let's bring up an assembly language one. Right here. Okay, this is an assembly language one right here. This is a text editor is what this is right there. This is a text editor. So this is where I write my code. But when I go back to these slides here, first we use an editor to type our program. Many excellent editors or word processors available to create that program. We don't do that anymore. The IDE does this for us. Today we use something called integrated development environment. It's called an IDE. If you look at this software right here, this is Silicon Labs IDE. It stands for Integrated Development Environment. So everything we need to do is in this screen, in this software package. That's there. Many assemblers follow the usual DOS, and they have to use the .asm. We still use the .asm if we're writing assembly. If we're writing C code, you would use .c. Actually, we don't usually use any others with the microcontroller, so it's usually .asm or .c. You might have a .include or a .h file if you're going to be using the .h is the header file for C code. That there, and what is that there? Right there. So, and .include is an include file for assembly language programming. That there. So, and we talked about those a little bit. Right there. So the source file is that there. Then it's fed to the assembler, right there. The assembler converts the instructions to machine code and produces an object file and a list file, right there. Now, that is done in our software, right here. If you push this button right here, that's the assemble button right there. If we push that button right there, it's going to create a list file right here. And let me go over here to this list file a little bit and talk about that right here. Now this list file right here is our code. Now as we go through this, the first thing you see right here, and I can't write on this here, I can highlight it, is you have this include right there. And this include tells the assembler to go out and get this file and stick it in here. Now this include file, all it is a list of all of our special function registers right here, along with their data locations right there. Now, if you notice that we have some of these that say active and some don't say active right there, it's because they use the same include file for a lot of them and they're not active for our particular compiler or processor right there. So, and we go through here, and you'll notice that right here, we'll talk a little bit about this one here. This is enable interrupts right there. That's a bit. So I can set EA. That happens to be IE interrupt enable port .7 right there. So I don't have to remember where the enable interrupt bit is. It happens to be IE.7, but IE is defined as memory location somewhere in here. Right here, IE is memory location A0A8. That's the special function register for the interrupt enable. So this is all our assembly. These are all our includes. So when you're troubleshooting your code, you're going to run into the situation where if you have an error and you look at the list file, and the list file is the easiest place to find errors and where they're at in your code. We haven't talked about list files. This is the first time I think I've shown list files right there. But right here is about where the list file ends right there. Right here. And this starts with the equates that I put in right there. So I have, in this particular case, I have 4 equates that we were using for our ad. I don't know if they're the same ones, A7, 78, 78, 3D, but we were using those for one of the labs out there. But that's our equates right there. Our green LED is port 0.1 right there. That's connected right there. So these are the ones that we put in. We put those in there. If I go back to my source code, right here, there's my equates. That's where they're at here, and then in the code itself, it's listed down here, right there. Those are just equates. Then we get into the reset and interrupt vectors, right there. We have an interrupt vector, reset vector, cseg at 0, and it's long jump to main. That's our reset vector right there. cseg at 0. This is our code segment right here. And now what you see here, this happens to be disabled. This is main. Now right here, we have 0000. Now this happens to be an address to be filled in later. But 75 is moved to memory location 97 DE. This is 3 bytes of information right there. That is my program. The assembler goes there and it looks for the instruction for move to memory immediate data. There's an instruction for it, and that equates to opcode number 75. What memory location? Memory location 97. What's the data? DE. The next one, we're going to move into the same memory location, the number AD, right there. Here, we've got moved to our crossbar XBR2, which happens to be memory location E3, the number 40 hex, right there. These happen to be our comments over that there. Here is logical OR is 43. Here's set bit 90 right there. D2 is set bit, and bit 90 happens to be the bit location for port 1.0 if we go back all the way up to our ports, and somewhere in here you're going to find our bit addresses right there. I'm not going to hunt for it, but the bit address is defined for port 1.0 right there, because that's a bit address, not a byte address. It's a bit address right here. So here's our bit definition. So if we go here, down here, we'll find somewhere there's a list right there. And I'm not, yeah, right there. I'm not going to, we're not going to hunt for it. But somewhere you'll find that location 90 is defined as port 1.0 right there. There's the start of our code. This is the start of our code. That happens to be an address that it's going to restore. Now we're going to offset that there. And here's again our move to R4, here's our code. Above that, these are actually supposed to be on the same line over here. I don't know why the formatting got screwed up. Probably if I unplug this, the formatting will look fine. It's that screen resolution. That's that. But you can see, as we're looking through here, that we've got an address here, and then we've got some code right there. Notice that move A to R2 only requires one instruction, FA. Right there. It only requires one instruction. Jump do not add, right there, is the instruction 78, and then 01 means it's going to skip one instruction, right there. This jump do not add there is going to look at the carry flag, and it's going to skip over. See, this do not add is an address, but the address equated to jump to done right there. In this particular case, we just skipped one instruction. right there. The jump to done means we're going to skip to the next one there. Do not add that there. So we can go through here and we can look at this right here. If we have any errors, they'll be in this particular code right there. And the rest of this is all just information on at the end. So going back to our slides, right here, is that we run it through, step one is we run it through the assembler and converts it into machine code. So we saw the machine code, it converts that there. It produces the object file and the list file. Now, when we look at the object file, it's garbage. I mean, the object file is in binary. There's that there. It's the same information, but all it is that there. And then we do one more thing, and we do the linking. The linking allows us to take multiple files and combine them together. Now, one thing we haven't done here is we can have a series of functions in one file. We could have our main code here. As long as we stick in here, we put in here some jumps over here, or calls to that there. Those will be unresolved at compile time, but then we link the two files together right there. So the linking is actually what generates the actual machine code right there. In our case, right here, this assembles, this builds, and build is another word for link right there. So this actually builds this. So link locate right there. So link locate, so that does that. If you hit this button, which is what I normally do, that does both at the same time. So now you might notice that sometimes you'll get an error on the link locate that says file not found. And the reason you get the file not found error, and let me just do this right here. You see, I get IO, error that there. The reason is that the linker can't find the file to do the link to link, and the reason it doesn't find the file is because the first half of the process is the assembly, and the assembly has an error right there. So now, sometimes you see this error and you don't know where it's at in the code, especially when it's long. That's where you go to the assembler here, and you go down, and you got to get past the include right there. Well, once we get past the include, we get to our code right there. And you'll see right there, that's where the error is. So in our case, it's easy to fix it right there. So, and I should point out that anything that's a keyword to the assembler, if your file's got a .asm name to it, it will put any keyword as blue. I think most of you figured that out now. Anything that's black means that it's something that can be whatever, and if it's green, that's a comment. So I can begin any line with a dash, or a semicolon. We'll put anything after that as a comment right there. So dash, notice the line turns green. A semicolon, the line turns green right there. So that's how we generate our comments right there. So again, we go through this whole process of linking, of assembling and linking is a one-step button. That there. When I say this was written in the dark ages, we used to have to type in DOS ASM51 space and the file name, and then we would type in link 51 space and then all the files we wanted to link together. Now, if we have more than one file we want to link together, under project we have add files to project. Right now we only have the one file there in our project, but we could have multiple files added to our project right there. So, all right, this part here is actually not important for this particular class because we're using the JTAG debugger tool that does this for us. But what comes out of the linker is usually two files right there. One is the ABS file. That's the actual code right there. Now, if we're doing this for like an IBM desktop, the file that would come out of the linker would be a .exe file right there. But that's our executable code. What we normally would then do is feed that through another program that will convert our hex converter that would then download to our ROM chip. That would be our code in hex right there. And that would be the thing that we used to type in by hand right there, the actual hex code. In our particular case, all we do is we connect it to the board and say download. That's there. So these slides actually goes through that there. Now it says, he did put in a note, I said this was written in the dark ages. Recent Windows-based assemblers combine steps 2 through 4 into one step. That's there. So actually, we're doing 2 through 5, or 2 through 4 in one step. When we hit that rebuild all right there, that does everything 2 through 4, actually. Rebuild all does steps 2 through 4, right there. Step 1, we still use the editor, but we use the editor built into the IDE, right there. The reason I go through these steps is, who knows, at some point you may be working outside of an IDE. Silicon Labs develops this IDE for their products. It works with their products extremely well. I have another IDE installed on this computer, and it looks very similar. Right there. And as soon as I can find it. And maybe it's on here. I know it's on here because it's, yeah, Code Warrior. There it is. See, this is another IDE right there. And I'm just going to right there. Let's open recently. Okay. Now, actually, I don't have any programs on this, but this is one here that this is for I installed it, but I haven't used it on this particular computer. I used this for other set of classes I taught right there. But this, I can just bring up here. This is a different editor. It looks very similar right there. Under project, we have make right here, which right there we can compile, disassemble. We have the similar type tools right there. So that's for the Freescale setup right there. So it's a different IDE. It looks similar, does similar things. The interface is that there. To be honest with you, I hate the Freescale, but I've taught some courses online for another university that used that, so I had that there, and I've used it for a couple of real projects. So I've used the Freescale that there, and they make the HC12 processors. For those who are old, ever heard of it, they're the old Motorola company. Freescale is. So they made the original 8000 family processors that Apple used to use Motorola products. So they were very popular for a while, right there. So again, we went through this process right there. Again, you use this here. You can look at this. These other files we don't worry about right there. But we go through this whole process right there. The linker actually is going to generate the file that generates also. The other thing that is not shown in here is there's the debug files right there. There's a file generated that allows us to debug our code and see and go through it one step at a time using the JTAG. If we were to actually burn the chip with just the code, then that information's lost right there. So again, this is the same type of thing that I went through earlier. It's optional, very useful out there. Where this list file comes in very handy, I should point out, is not so much for this class, but when we use C, the C compiler generates code that is not one-to-one compatible, or that there. It's kind of like you use a GPS to get from my house to the campus here. I live near Staupak here, down in Dakota. I can go two ways to work. I can go John Gombach around in this way here, or I could go over and jump on the MR2 and take that way around. Both ways are very similar distances, similar time frames. Right there. Which way I take depends on my mood at the time. I almost always take John Gombach because I hate the MR2 because it jams from time to time. That there. But regardless, that there, if you use a GPS system, that there, the GPS system, such as Waze, for example, takes in some data that I don't have. That there. And it takes into consideration traffic and feedback that people have given that there. So, but when we look at a GPS system, we're going from point A to point B. There's 4 different routes of going there, right? All 4 routes will get us there. Which way is the quickest? Some computer programmer sat down and mapped out the various routes. There's an algorithm that they use, a mapping algorithm that looks through this route. This street here, it's given a weight, this street, and it finds the route with the lowest score, and that supposedly is the fastest way. Programs such as Waze and Google Map now takes into consideration traffic that there. So this road here may have a score of 3, but if traffic is heavy, it may go to a score of 7, for example. Right there. This road may have a score of 4, but it goes to a 6 when traffic's heavy. So if traffic's heavy, it'll take you this way. If traffic's light, it'll take you this way. Right there. Well, compilers do somewhat the same thing, only they don't take into consideration traffic. They just take into consideration the mood of the programmer and what their preferences are. And when we write assembly language code, ASM to hex code, it's 1-to-1. In other words, there's only one hex file that's going to come out of a particular assembly language code. We're specifying strictly move into the number 35 hex right there. There's only one set of opcodes for that. 75, I don't know what 75, we'll say 7631 is the code for that. It's good right there. When we go from C to hex, there are many paths that you can take and get to the same code right there. And one C instruction, A is equal to B times C, where A and B and C are all defined as long or 16-bit variables, right? So this is one line right there. Well, this is exactly what we spent 2 hours working on yesterday in assembly. And that becomes one line of C. So obviously, one line of C is going to equate to a whole bunch of assembly language code. And the code may not be unique from time to time. We may be using registers up here that aren't available down here, so we have to use memory this time. Another time we have this line, all of our registers are available, so we use the registers. So even with the same compiler, you don't get the same instructions every time. because some resources may be in use already. So as a result, when we go through a compiler, when we go to C and we go into our processor, right there, and we're debugging, we debug in assembler. We use a disassembler to see the code that we're at there. When we're going through it, we're traversing through our code, we may see in our C code that we stay here for many clock cycles. But over here in our code window or disassembly window, we're going step by step. This one instruction can be 100 instructions in C. You know, I just used the example. A is equal to B times C, right there. That is how many instructions did we have yesterday? 50 instructions if you count the number of lines total in that program, right there. So that's why when we're dealing with C, this list file becomes a little bit more important, because we can also see what C assembly language code is generated by the compiler, right there. So the compiler will generate code. All right. The programmer counter points that we talked a little bit about that. The program counter is 16 bits. We don't write to the program counter very often. I mean, we never write to it, right there. Starts at address 0 when they're powered up. This is our reset first at there. Looks to the first instruction, and so we use the org to stick that in there. Org 0, right there. Now this particular piece of code is actually not what we would write very often, because this piece of code doesn't have the long jump to main and just has our code right at the top. So we lose all of our interrupt vectors and everything else. So if you write your code this way, you can't use interrupts. So normally you would do the code the format that we're using, the template, is a little bit more flexible. This is the old way of doing it, where we didn't worry about using interrupts up there. But all this is saying here, this is just going back here, that 7D is moving to R5 immediate data, 7F is moving to R7 immediate data, 7.4 is moving to 0 or A immediate data, 2D is add R5 to A, 2F is add R7 to A, 2412 is add to A12. So you can see the first byte here, right here, the first byte equates to move into R5 immediate data, and then it's followed by the data right there. And this is what we used to do by hand, right there. That's the output of our assembler right there. And I'm not going to spend much more on that there. Let's kind of go through that there. And you can watch through that on the code when you go through the single stepping. Right there. You can see a step through the code, but if you open up the code memory window, you can actually see those instructions being executed right there. Right there. Okay, just kind of a note here that in the code family, no member of the 8051 can access more than 64 kbytes of opcode. That is not true today. Silicon Labs and a couple other vendors have found ways to generate code pages. That's there, and there's a trick around that. So you can have code up to 128K of code now. I have multiple pages. Right there, we won't worry about this class right here. So, that there. Only has one data byte, we talked about that there. Okay, this particular right here is now we're setting up a variable, and this is in location 500 hex. We have to assume that to be in the code segment, because our data segment can't go any further than that, right there. That there. So this is in our code segment. Right there, and data 1 is defined as a byte in the number 28. Data 2 is defined as a byte. This has got a B and this is an H right there. Here we define data 4, and this is an ASCII 2591. So that's going to assign 4 characters. That there, and they're 8 bits. So that's defining 4 bytes right there. This one here is my name is Joe is also another way of defining. So what we're doing here is we're defining there. These are just labels for our data right there. so that we can say move into A the data at address data 1. And then we could move into A the address at data 4 plus an offset. You know, in other words, we would have an offset. That there. We would load A with the address of data 4, and then we would use, or the data pointer, we would set the data pointer to data 4, and then we use an offset to traverse through that there. So this is how we define data right there. The org, we talked about end, is pretty obvious right there. Equate, we've used the equate plenty of times, right? Everyone knows the equate. Count, equate, move. Now notice that the equate replaces the word 25 with the number, the word count is replaced with the number 25. You still have to put the pound sign in front of it, or hashtag. I grew up with that being the pound sign, and then some people call it the number sign, and now it's the hashtag, right? So I'll use that term pound sign, hashtag, and number symbol all interchangeably, but that just means immediate data. But the word 25 is replaced by the number, or the word count is replaced by the number 25. So if you don't put the hashtag there, it's going to move into R3 the contents of memory location 25. Just as the mistake I made the other day when I left the pound sign or hashtag off the 0. It loaded into the accumulator, or in the address 32 and 31, it loaded the contents of A, or memory location 0, not A. And there, so the pound sign is very important. That there. So this is the constant used. Okay, I'm getting into some new material. How am I on time? I think I'm in great shape on time. Oh yeah, we got another 20 minutes, 30 minutes I can talk. I can't talk that long, so don't worry about it. My throat's not there. Okay, the program status word we've talked a little bit about. I want to go into a little bit more detail. This is that there. No. I understand these. That there. All right, the program status word is also called the flag register. That's where our flags are kept. Now, one of the things to keep in mind that the flag register is also used to change the register banks. That's there. Thus far, we've only been using register bank 0. We'll probably start changing the register banks a little bit to give us a little bit more flexibility. We could change register banks on the fly by simply writing to the program status word right there. So 6 bits are used. 4 is the carry flag, the auxiliary carry, the parity, and the overflow. So far, we've only used the carry flag right there. The carry flag is set whenever we have an addition or a subtraction that goes outside the 8-bit register. So in other words, if we subtract 2 numbers and we have to borrow there, then we use the carry flag is set when we borrow. We add 2 numbers and the answer is greater than FF, we set the carry flag right there. The auxiliary carry flag is set if we have a carry from the lower nibble to the high nibble. When I say lower nibble, we've got 1101, 1011. We do an add 1000. When we add this is 1100, and we have a carry. This is the auxiliary carry right there, because it sees this carry from this here to here, right there. Now, most of the time we can ignore the auxiliary carry. The only time we worry about the auxiliary carry is if we're trying to work in BCD. Because binary coded decimal means that we have an auxiliary carry, means that we have to add 6 to it in order to get the correct answer. So, for example, if we have BCD, BCD is binary code decimal. So so BCD only goes 0 to 9, right there. You know, if I add the number 35 to the number 27, for example. Now, if you do normal addition, this is going to give you 2 with a 1, 3, that's 10, 11, right? Or no, excuse me. This will give you 6 right there. Yep, that's fine. I'm trying to do multiplication here. I've got myself all mixed up. So this is the right answer, 62. You get around microprocessors long enough, basic arithmetic becomes difficult. That there is, you sometimes see me struggle because I tend to think that there. But this is the right answer. But if you do this in binary, 0011, 0101, 0010, 0111, what you get, 1 plus 1 is 0, 1 plus 1 is 0, 1 plus 1 is a 1, 1 here. Now in this particular case, we've got the number 12 right there. So that's an illegal BC number. We go ahead and we add this here, we get 1, 0, 1, 0. So right here we've got 50, 12 is A, B, C, right? 5C. That's not, we can't use that. So we realize that we got an illegal BC number, so we add 6 to it right there. So when we realize that, we just go ahead and we add 6 to that, and that's going to give you 0, 1 right here. This is going to give me a 1 with a 1, 0, a 1. That's going to give me a 0, 1, 1, 0. That's going to give me my 60. This is a 0 right there. Yeah. So yeah, 62. Yeah, I had a 1 here. Yeah. So as soon as I saw the wrong answer, I realized that I made a mistake there. So this is 62 right there. So by adding 6, I corrected it right there. Now that's one case. If I have the other case, 0, 1, 0, 1, 0, 1, 1, what? 1, 0, 0, 0. So in other words, in this case, 0, 1, 0, 0. I'm going to be adding 57 to 28 right there. I'm going to be adding that there. Now, in that particular case, that's not going to work here. I'm going to come up with a different example. Right there. Let's add 59 here in this particular case right here. I'm going to add 59 there. So when I add those up, that should give me 787, right? Does that look right? All right. When I do the addition here, I get 1, 0, 0, 0, and a carry out right there. So then 0, 0, 0, 1 right there. Then I turn right around, and because I had the carry out, I add my 6 right here. And then I get my 1, 1, 1, 0, 0, 0, 0, 1, 87. So this carry out tells me that I have to add 6. So I've got two situations. One is if the lower nibble is greater than 9, I have to add 6. Or if I had an auxiliary carry, I have to add 6 right there. So, and the same thing, if I have a carry out, I have to add 6 to that bit there. So that's where the auxiliary carry comes in. I'm not going to worry too much about that. There is also a command called decimal adjust that does some of this automatically for us. Because that's the number of characters you skipped. You're going from base 16 to base 10. So you have 6 extra symbols here. So when you have the carry out, you need to skip over the 6. It's the difference between 16 and 10. That's where that 6 came from. Right there. So, and some of that should have been covered in basic digital, but I'm teaching basic digital and I skip over it too, so that's there. But that's where that auxiliary carry comes in, is if you're dealing with BCD, right there. So the other 2 bits, unused bits, are usable, definable. These are PW4, RS0, and are used to change the bank. So as we look at these right here, this is the program status word. Here's our carry flag, our auxiliary carry flag, F0, I can't remember what that one is right there. This is our overflow and our parity. F0, I can't remember that there. Set that there. The parity is set to 1 or 0 in order to indicate whether it's even or odd in the accumulator. That just simply tells us what the parity is in the accumulator. The overflow is if you have an overflow at there, which we haven't talked about there. This right here, these are our 4 register banks, and we set those RS0 and RS1. 00 is the default. 01 is bank 2. 10 is bank 1, bank 2, and bank 3. So that's how we change our banks. That there is, we would set those flags accordingly to change what's set. Because if you look at, and jump here ahead, they don't, here, okay. If we look here, here's register bank 0, 1, 2, and 3 right there. And they're each 8 bits there. Now the default stack pointer is right here, bank 2. So you don't want to use bank 2 typically. But those are, once you change those banks, you get more efficient instructions. Remember, you can move to R0, move A comma R0 is one instruction, one opcode, versus using a memory location right there. Now, you can also address the registers as memory, which something that I didn't really point out that there, but when I did the move 31 hex comma 0, I was actually moving R0 to 31 because memory location 00 is R0 right there. So when I said that R0, location 00 is random, it probably wasn't random at that point because we'd already been using R0. So R0 and memory location 0 are the same place right there. Memory location 30 is the start of our scratch pad RAM right there. So as we look at our memory, there's a reason I started at 30, 31, 32, 33. I use those 4 locations because this is what we're supposed to use for scratch pad RAM. It's those locations there. We can use 20 to 20F. There's nothing says we can't use those locations. Those are perfectly fine locations. That's there. It's just that we can also use them as bit addressable locations. That's there. So this particular block of RAM, that's 16 bits, 16 bytes, is very flexible because we can use it either bit by bit or we can use it byte by byte right there. Anything above that, from this 128 bytes, we have to use as only bytes. So I've used starting at 20 many times. If I don't have a need for bit addressable memory, then I just start at 20. But if you think you might need bit addressable memory, then you can start at 30 right there. And everything from here, these are our register banks. And typically they'll start the stack at 0 or at 08, and depending on how much you use the stack. The stack is used for calls and interrupts. We'll use the stack. We haven't talked much about the stack yet, right there. So, So again, this is our format. These are the instructions that affect the register, the carry flag. As you can see, there's add with carry, subtract, multiply will affect, divide, decimal, add, adjust. These are rotate, right rotates, left rotates, right there through the carry. Set the carry bit, clear the carry bit, complement the carry bit and the carry bit or the carry bit, move the carry bit out, and set the carry and jump not equal right there. So these are the various things that set that. We also have the overflow and the auxiliary carry set here. So I don't use this one very often right there. I don't use that one very often. I don't use this one very often. The carry flag, as you notice, we use a lot right there. So again, this just shows how to use a carry flag. I'm not going to worry too much about the carry flag right there. I talked a little bit about the auxiliary carry. The parity right there since the accumulator has an odd number of ones, that there it's set to 1. So the parity flag, if there's an odd number of ones in the accumulator, it's set to 1. If it's an even number, there are cases where you would use the parity flag. That there, I can't think of any off the top of my head. That there. So, but show the status after that there. And these make really interesting test questions, by the way. That there, these examples that they're, you know, they make, because they're fairly straightforward. Because this is, give me show the status of the flags and the accumulator after the following set of instructions right there. So when you look at possible final exam questions, these examples, have I posted this up on, have I given you this here yet? Have I given you this right there? Let me see if I've got Wi-Fi. If I've got, let me, yeah. Remind me to post this on Facebook that there for you, that there's, because it's probably worth it for you to have those slides. As I'm pointing out certain slides, and as I review for the final, I'll probably go back and highlight slides that'll be on that there. I don't get Wi-Fi in this room, so that there. So. It may. Right there. Yeah. As soon as I get back up to the office, I'll post. When I post the video, I'll post this file out there. So, again, it's just simply a matter of knowing which ones are there, and I'm not going to go through each and every one of these up there. Okay, there are 128 bytes of RAM in the original 8051. Remember that the top 100. There's actually 256, but remember what they don't show here is that starting at 80 going to FF are our special function registers right there. Right there. Those are our special function registers. So if we look at the 8051, there's only 128 bytes of available RAM, of which 32 bytes are used up by our banks, register banks. So we really only have a very small amount of RAM to play with. Now, remember that our processor has XRAM available to it, X memory as well, that we can write to. So, default, right there. This just simply shows, again, this is, I said R0 right there, just simply shows the memory locations for our 4 banks right there. This is where we set our use of select at there, right there. So again, we can, right there, again, what we're doing here is move load R0 with number 99. These are just our moves to our, here, this is just showing that this is the same as that right there. Now this here is set bit program status word. That's telling it that we want to select. We're setting this bit right there, PSW4. We're setting that to 1 right there. You probably, if you're going to be doing that, you probably ought to clear bit PSW3 right there to make sure that both of them are set right there. So this is assuming that both 3 and 4 are already 0. So this is setting to select 2, and I'm saying if you're going to be changing bits, it's a good habit to change both bits, right there. Because if, for example, I was using 1 and I set this bit, now all of a sudden I'm on 3, because I only set this one. So I'm saying you should also clear that one, make sure that one's clear as well, right there. So it's just, you know, it's just a good habit to get into. Because then that just changes the location right there. So let me talk a few minutes about the stack, and then I'm going to probably wind up there. The stack is used to store information. The stack pointer is only 8 bits wide, so it can take a value between 0, 0, and FF. right there. Upon power up, it goes to location 7. You know, so that's why I'm saying bank 1 is already being used for the stack. So the only time you use the stack is if you do a call or if there's an interrupt. And the first location. So the stack is used, and what we do is we push things onto the stack and we pop things off. As we push data onto the stack pointer is incremented by 1. This is different. Many processors, the 8088, for example, or the 8086, will increment the stack pointer by 2 because it pushes 2 bytes at a time. Here, because we're using strictly an 8-bit registers, we're going to push 8 bits at a time. Loading the contents of the stack back is called a pop. So we push and we pop. Now, the stack uses a last in, first out. That means that if I push A, push B, push R0, push R1, I do some code, and then at the end I want to pop it back out. I want to restore these. Because the whole idea of the stack is that I want A, B, R0, and R1 to be equal to the same thing when I go back, right there. So I would pop R1, pop R0, pop B, pop A. So we reverse the order right there. This order is reversed, see? This is the last thing I pushed in, so it's the first thing I pop out. This is next to the last, it's the second thing I pop out. So we do it in the reverse order. We push it in 1, 2, 3, 4. We pop it out 4, 3, 2, 1. We just simply reverse the order. So the stack pointer here points to here. If we push that there, so then it moves to here, then it moves to here, then it moves to here. We don't adjust the stack pointer ourselves. We don't change the stack pointer. It's set for us. Now, if we want to move the stack pointer somewhere else, we can do that. We can load the stack pointer, say with address, 50, for example, because we need it to be longer than 8 bytes. In other words, right now it's pointing to location 8 right there. Or, well, it's pointing to 7, but the next place it's going to put to is 8. This is actually R0 bank 1 right there. It's pointing to that right there. So the first thing we point goes to location 8. Next thing we go to 9 right there. And it just keeps going down as it points right there. But if we're going to need more than 8 places and we're going to use the banks, we can move it elsewhere. Right there. But typically this is just kind of showing here, we're moving 25, and we're going to push 6, push 1, push 2, and push 6. Oh, okay, this is push 6. It's doing the location. It's 25, 12, 4. This push R6 is the way I would write this. I wouldn't push 6. I would put the R6. It's a little fuzzy the way that he did that there. He left the R off right there. But remember, it's the same thing. Remember, location 6 is R6 if we haven't changed the bank. So, and all this is just showing is that 8, and we just keep moving it up that there. So we push, put the next one there. So then we pop it out in the reverse order right there. This is pop right there. Use the R3, pop 3 up there, pop 3. Now notice though, pop 3, it's putting, and this doesn't really show, it just shows the stack pointer changing right there. It doesn't show the locations where it's going right there. I'm going to stop at this point right here because we're now getting into the call instruction right there. And I think really at this point I'm at my hour and 15 minutes there, almost perfectly.